Hi. So firstly, I'd like to thank the organisers for giving me this opportunity to present my work at this year's edition of Cosmology from Home. Right. So my name's Theo. I'm a third-year PhD student at Queen Mary University of London. And I'm going to be talking about work that I've done in collaboration with my PhD supervisor, Tim Clifton. This work is summarised in the paper, whose archive number you can see on the screen. And the title of my talk, as you can see, is Modelling the Emergence of Cosmic Anisotropy from Nonlinear Structures, which is a little bit of a mouthful. But I hope that through this talk, the meaning of each of these terms in the context that I'm thinking about the men will become clear. So the motivation for this work largely comes from a series of interesting observations that are disputed and often controversial, but which are of possible signatures of anisotropy in the universe on large scales. So where the universe may not be best described essentially by a Friedmann-Lemaitre-Robertson Walker or FLRW metric. So in this plot, which is from a paper by Wherein and others from last year, you can see the direction on our sky of a variety of observations of potential signatures of an isotropic universe. So, for example, the cosmic microwave background dipole, dipoles in cosmological parameters, or in supernovae observations, and so on. And in sort of by eye, you can see that there's a rough direction upon which these seem to lie, which tells us that a model of the universe where we have a single direction of anisotropy along this kind of direction might be an interesting thing to study. And if we are going to study such a universe and develop our cosmological modeling for this, then we need to understand how these cosmologies work and how they might be sourced. So this kind of moves us on to the question of, well, how actually do you build a cosmological model? And specifically, how do we build one that might be more general than just our standard FRW picture? So the standard way of doing this that I'm sure you're all familiar with is that we assume some kind of cosmological model as our so-called background. So typically that would be FLRW, but it could be something anisotropic, such as a Bianchi type universe. And then we take observations, say, of cosmic microwave background or supernovae and so on, and we use those observations to fit some model parameters, and that then describes our cosmology. And then when we see structure in the universe, we use perturbation theory to describe that inhomogeneity, and from that we obtain observables such as a matter power spectrum and so on. But there were a few issues here. So one is just a pure science one that we would like to test if this FLRW or standard model picture is self-consistent, and it's difficult to test it if you assume it from the start. The second is a sort of a mathematical point, which is potentially, although it sounds very technical, of some serious physical significance, which is that in general relativity, which is a non-linear theory of gravity, and as far as we can tell is our best understanding of gravity, the evolution of the average, by which I mean this sort of average metric in the angled brackets that sits on the left-hand side of our Einstein equations, is not the same as the average of the evolution, by which we mean the metric that one would obtain by taking the full Einstein equations, averaging the matter, and then solving those equations for the metric. So that means that if we assume that a certain cosmological model, say FRW or Bianchi or whatever, then the effect of small-scale structure can't generally be ignored. The fact that we have inhomogeneity in the universe means that when we do our homogeneous large-scale model, we may have signatures that are changing or biasing our measurements. So we want to build our model for anisotropic cosmologies. And it turns out that this kind of seemingly esoteric mathematical point is actually really useful in this context. Because if we take the standard anisotropic but homogeneous cosmology, such as the Bianchi classes, these often get more isotropic at later. So if we want to be consistent with the CMB, which we know had to be highly isotropic, that tells us that it can only have got more isotropic since then. But if we want to describe, for example, a dipole in the matter distribution or so on, so some signatures of large scale, late time anisotropy in the universe, clearly there's going to be a problem there. We need some way of sourcing these effects at late times in the late universe without messing up our CMB observations. And it turns out that this averaging procedure will be of use. So how does this work? So it goes back to analysis that was originally made by Bucket in the 1990s. And the basic idea is quite simple, is that take our universe, divide it up into constant time slices through some time like normal vector n, in this diagram here, and then evolve the universe from slice to slice. And then if we take a patch, spatial patch on those slices, we can define an effective scale factor, say, from the volume of that patch or that domain. So if we evolve in time, we can see how the volume of that domain changes, or the expansion rate of that domain, or the average energy density in there, and so on. And therefore, we can construct what the effective kind of cosmological evolution that an observer in that domain would see. So, for example, what one finds in that case is that potentially you can have acceleration. So the effective scale factor measured inside that domain has a positive second derivative, or a double dot over a is greater than 0, if this back reaction term Q is sufficiently large. So if we have this isotropic expansion theta, and if that has a sufficiently large variance, for example, then this Q can be very large and positive. And therefore, even if we just have non-relativistic matter, we could still potentially be seeing some acceleration, or at least deceleration parameter might be slightly less negative than otherwise thought from a kind of a naive FLRW picture. So this is what's known as back reaction. This is the idea that the inhomogeneity, which is expressed, for example, through this variance term or through the shear and so on, that this inhomogeneity has some effect on the large scale expansion. So we're going to apply this same logic, but now looking at an anisotropic model rather than a purely isotropic homogeneous FLRW one. So we want to build a model for universes that are statistically homogeneous, but they have this single direction of large scale anisotropy that I talked about in the context of that diagram on slide 2. So these are a very specific class of cosmological models. They're called the homogeneous and LRS, or locally rotationally symmetric. A lot of work was done on them by Ellis, for example. And the homogeneous anisotropic cosmologies that these ones fall into, as I said, usually isotropized. But if we exploit this averaging scheme, we can see how that picture may change once we consider the effect of inhomogeneity. And for example, we might be interested in whether the anisotropy, or some measure of that anisotropy, actually grows at late time because of this inhomogeneity. So you carry out this full formalism, and you have to do quite a lot of maths, but you arrive at some interesting conclusions. So I'm just going to present one equation here. So in this case, what we're trying to think about is this term Q, which you can think of essentially the momentum of matter with respect to a constant time slices. So this is like a bulk flow, large scale coherent motion of matter. And this theta is essentially the expansion rate. So it's like 3 times the Hubble factor would be the kind of equivalent in an FLRW universe. So what you can see is that if we ignore these terms, which are generally quite small, and if we ignore the back reaction, which is the scale of B11 on the right-hand side, then this Q is pretty much always going to decay because of the presence of this Hubble parameter. So Q dot is going to be less than 0, and it's going to decay away. So we will go back to isotropization at late times, which is the picture in that homogeneous case. But if we have an homogeneity, then we have a variety of effects from, say, gradients of different matter or curvature quantities, from variances and covariances of different effects, such as the expansion rate or the acceleration of the observers and so on. So this picture could be quite different. And of course, you need to do some detailed analysis to determine the functional form of this back reaction and to see whether it's large enough to source the bulk flow or the whatever other measure of anisotropy, for example, a shear, that you might be interested in. But you can see that the conclusion can be different, at least in principle. Of course, in order to get specifics, you have to apply a specific model or do simulations and so on. So I will show you one model where you can actually calculate these back reaction scalars exactly. So this is from a set of cosmological models by Farnsworth in the 1960s. So these are exact homogeneous spacetimes, but they have a bulk flow. So the slices of where the space is homogeneous are not the same as the ones that are orthogonal to the flow of matter. So just general observers that move with the matter see a bulk flow. They think that there is inhomogeneity in their universe, and therefore if we're averaging those rest spaces of the matter, which feels like the most natural thing to do, then you would see back reaction, even though there is this exact homogeneity. So you can see how we have to be very, very careful with the conclusions that we draw in a universe where we have bulk flows or anisotropy and so on. So in this case, you can see that, for example, the back reaction on these four quantities that I've plotted. So we've got the expansion, shear, and then a couple of other quantities. So if you look at, for example, at the back reaction on the expansion rate, which is this brown curve, you can see that it starts in some case of the parameters of this toy model. It starts off with quite a large back reaction of, say, around 10%, but then quickly decays to 0 at late times. And that's because, in this case, the only inhomogeneity is coming from this bulk flow. And as that bulk flow decays away, we return to a pure Friedman-like universe. So in that case, we certainly wouldn't see anisotropization at late times. But as a first step, this is an important way of seeing how these effects work. In summary, what have we done? Well, we're interested in describing a cosmological model that has an anisotropy on large scales. So we've chosen the homogeneous, locally rotationally symmetric cosmologies as an appropriate model for the universe on large scales. And what we found is that when you study that large scale evolution, it is sourced by a series of back reaction types. And it's these back reaction scalars that can source the anisotropic expansion as well as the regular isotropic Friedman-like expansion that we see in the universe. And of course, more analysis is required to think about what the observational signatures of these kind of effects would be. And that's something that we're working on and looking to develop further. So for further details and the technical mathematical formalism, I refer you to the paper. And thank you for listening. I'll be happy to take any questions in the discussion session. Thank you.